What we're going to get into in this lesson is called two variable statistics. So instead of just isolating one variable and looking at the mean and the median and the standard deviation, different measures of central tendency, different measures of variability, box plots, histograms, pie charts, different things for categorical quantitative variable. Uh, Two variable statistics focuses on examining the relationship between two quantitative variables. Now, you can probably tell by how deliberate I was in presenting that this is extremely important. Again, tattoo this into the brain. Scatter plots and correlation, this whole two variable statistics that we're studying in lesson number 2, examines the relationship between two quantitative variables. So the first thing we talk about, generically speaking, is just correlation. And a correlation exists between two variables when there's a relationship or when the two variables are associated. Again, tunnel vision on what kind of variables? Two quantitative variables. Now, a linear correlation is a specific type of correlation where the relationship or the association between two variables is best explained by a linear model. The first thing that we typically look at or examine is called a scatter plot. And a scatter plot is just a graph of the paired data. And you've probably seen these things ad nauseum where the horizontal axis is used as the x variable, the vertical axis is used as the y, and we plot our points. More about that in just a second. Now, an example, weighing seals with a camera. In this problem, I see that my horizontal axis is overhead width. Again, huge, huge, important stuff. All right, so get this in your notes. The horizontal axis is called the overhead width. The vertical axis is the weight. The horizontal axis is the independent variable. The horizontal axis is also called the explanatory variable, and the horizontal axis is also called a predictor variable. The weight, the y variable, the variable that's on the vertical, is called our response variable or our dependent variable. So this point right here that I am circling has an x value of about 8.4, and it has a y value of about 175. This point right here that I'm circling has an x value about 7.2, and I'd say it has a y value approximately, I don't know, 118, let's call it. Now, what we typically want to do is we want to eyeball a couple of things when we're examining the relationship between two quantitative variables and we're given a scatter plot. Well, the first thing we want to look at is the direction. And if the direction, the general direction raises to the right, then we have a positive relationship. If the cluster of points kind of fall off to the right, then we have a negative relationship. If there's just a bunch of clutter of points there where there's really no positive or negative direction, then we say that we have no relationship. Let me give you some examples. Heights of presidents and heights of their main opponents. I see no correlation here. I don't see any distinct pattern where there's a positive relationship or a negative relationship. So by default, this relationship would be described as no correlation. And what we see with a scatter plot that exhibits no correlation, this eyeball typically just tends to be best fit. And we actually call that the line of best fit. The line of best fit is just a horizontal line. Now, on the other hand, we could have something that is a negative correlation. So a negative correlation tells us that as our X value increases, so look, this arrow right here means that our X's are getting bigger. And as our X's get bigger, we can see that there's a decrease in the Y values. So that's a characteristic of a negative correlation. Our X values decrease, I'm sorry, our X values increase and our Y values decrease. Now, what would a positive correlation look like? Well, it'd be just the opposite of that, right? Our X values increase and our Y values increase. No correlation. What does that tell us? As our X values increase, there's no discernible pattern. Y values could be increasing, they could be decreasing. There's no value, or I'm sorry, there's no pattern in the way that the Y values are related. So a correlation summary, if the line that we eyeball raises to the right, we have a positive correlation. In other words, as one variable increases, so does the other. A negative correlation, as we move to the right, our pattern of data decreases. That's called a negative correlation. In the bottom plot, there's just no linear association, so we say that there's no relationship between the two variables. Now, after we eyeball, we want to fit what's called a correlation coefficient to the scatter plot. Now, correlation coefficient is denoted by lowercase r, and it is actually a value that corresponds to and tells us, gives us additional information about the strength of the relationship between the two variables. Now, a linear correlation coefficient tells us the strength of the linear association between two variables. So we have floating out there this generic concept of correlation coefficient. What's it do? It examines the relationship between two variables. A linear, excuse me, a linear correlation coefficient examines the strength of the linear association between two variables. In this case, in this class, I should say, our focus will be on the linear correlation coefficient. A couple of facts about the correlation coefficient, the linear correlation coefficient. The value is always between negative 1 and positive 1. If the sign is negative, that means that we have a negative relationship. If the sign is positive, it tells us we have a positive relationship. If R is really close to negative 1 or really close to positive 1, then there is a correlation. If R is close to 0, then there is not a correlation, a linear correlation. Let's take a look at some. Scales are all the same. The first graph there would have a correlation equal to 1. Why? All of the points are on a single line. And it raises to the right, which means it's positive. The next one, notice how the points start becoming distributed a little more. Again, imagine there's a line going right through the central focus of this data. As these points start to spread more across the line, this value will decrease. So from here to here, it decreases to about 0.8. Notice there's more variation here around that line that we can visualize. Notice the R value decreases and heads towards 0. In a situation like this, we have a lot of deviation around that line that we can eyeball, so the correlation will go even less. Now, the previous, let me go back. Okay, this will work. This correlation right here would have, the correlation coefficient for the bottom would be equal to 0. I would estimate this correlation as being probably 0.8. I would estimate this correlation as being probably negative 0.8. And I would estimate this at being close to 0. All right, a little bit more. Notice the upper left. You can't really tell it because the typeset's pretty bad, but this would be negative 0.9. Why? Well, it's decreasing. This would be negative 0.5. Why? Well, it's negative because it's decreasing, and there's more spread around that line that we can visualize than there is here. And this would be 0 because there's no discernible pattern of positive or negative. Positive raises to the right. Again, there's quite a bit of room from that line that we visualize. Less distribution of the points, so higher correlation. All of the points are on a single line, positive slope, so our correlation is 1.0. Now, the next thing we do in correlation and regression is we fit that line. That line that I told you, well, we just kind of visualize it. Well, there's more to it than that. So that line is actually called our regression model, or our regression line, or our regression equation, or the line of best fit, or the least squares model, the least squares line. All of these descriptors uh, align with the straight line that best fits the scatter plot of the data. I actually teach a class on this at the graduate level for our master. Actually, I teach two classes on this, but it's an advanced regression class, and we dive into the calculus behind all this. So there is a method to the madness, if you will, of the way that we actually find the equation of this line. It actually uses matrix operations, but for you guys, you don't have to worry about that. When you want to find this regression model, you're going to plug your information into StatCrunch. You're going to click the buttons that I'm going to teach you to click, and your regression equation will be right there. So the bottom, the regression equation is y. Now, this part right here is called y hat. This y hat is called the predicted y. So we can predict y equal to beta 0 plus beta 1, I'm sorry, b0 plus b1 times x. The primary purpose of a regression equation is to explain our relationship and use it to make predictions. Let me repeat that. Primary purpose of the regression equation is to better explain the relationship between x and y and to make predictions. Now, this model, again, what is y hat? Predicted y. What's beta b0? That's the y-intercept. What's b1? That is the slope. So the regression line here, I can tell you that the y-intercept, I can take this down to see where it would cross the y-axis. So I would estimate that the y-intercept would be about 158, and the slope would be positive. And if I needed to come in and get a couple of points there and calculate the slope, get an estimate of the slope, I could do that. But again, you don't have to do that. You're going to plug your data into R, and it's going to create the slope and the intercept of this regression model for you. All right, a little bit more about the regression line. I would file this under what most people really don't want to know. Far too much information, but it's stuff you need to know. You got to think that if, let's say, for example, I want to examine the relationship between a student's high school GPA and their first semester college GPA. Well, I would create a regression line. Now, if I'm making a statement about everyone, every single person who, let's say, is in college this year, so we're looking at their high school GPAs and their first semester college GPAs, then I would be talking about everyone in my population. Well, I probably couldn't measure everyone in my population, so I would take a random sample and from our population and calculate the estimates of beta 0 and beta 1. Those estimates are B0 and B1 respectively. B0, the intercept for the sample, estimates beta 0. B1, the slope for our sample, estimates beta 1. Now, we're going to get into this a lot more in lesson number 7. For right now, I just want well, I guess I want to be able to crawl, and we'll run a marathon in lesson 7. So Beta 0 is the intercept, and beta 1 is the slope. And again, we'll calculate these values using StatCrunch. So an example of a regression model may be y hat. So the predicted value for y is equal to 80.9 plus 2.3x. The intercept is 80.9. The interpretation tells me that when x is equal to 0, the predicted y value is 80.9. Makes sense, right? If I come up here and put 0 in there, what's 2.3 times 0? Oh, it's 0. What's 0 plus 80.9? Well, it's 80.9. So when x equals 0, the predicted y value is 80.9. The slope is 2.3. This tells us that as the x increases 1 unit, the predicted y value increases 2.3. Now, what if we had a regression line, but the slope was negative instead of positive? The interpretation of the intercept doesn't change. Still, when x is equal to 0, the predicted y value is 80.9. The slope, however, and that should be the slope is negative 2.3, says that as x increases 1 unit, the predicted y value decreases 2.3 units. So make sure you understand that's a typo right here. This should say the slope is negative 2.3, not 2.3. My mistake. So the last point that I want to make, again, what is a regression line used for? Twofold. It's used to better explain the relationship between x and y, and it's used for prediction. So if our regression model is y hat equals 80.9 plus 2.3x, we could predict y when x is equal to 10 just by inserting 10 into our model and multiplying and adding. So our predicted value would be 103.9. All right, gang, there's a lot more to it. Get into residuals, we get into, I'll get into a lot of stuff. But I think it's a cool concept. Um, and again, let me circle back and give an application of the regression line. Let's go back to where, X is the high school GPA and Y is the first year college GPA. I could take a sample of students and I could create my regression line. Y hat equals whatever plus whatever. I don't know what the slope would look like. I don't know what the y-intercept would look like. I would use technology to create those estimates. But then let's say that I have a student who comes to us with a high school GPA of 2.7. Well, I could put 2.7 into our model and predict their first year college GPA, or I'm sorry, first semester college GPA. Well, what if the predicted value was 1.8? Well, then maybe I should develop a system, a program at the university that gives that student extra support. What if the predicted first semester GPA is 3.9? Well, maybe I want to give that person a scholarship because they're very, very, very likely to succeed at the university. So anyway, a lot of application opportunities, options for two variable statistics, specifically correlation and regression. All right, gang, that's all I got.